Today we're going to look at another special case of solving particular finite matrix games, and we're going to look at the case of a symmetric game. What do we mean by symmetric game? Well, the formal definition is that a finite symmetric game is just one in which the matrix A for the game is skew symmetric. What do we mean by skew symmetric? It means that A is equal to -1 times its own transpose. Why would we call this a symmetric game? Well, the idea behind a symmetric game is that both players, player 1 and player 2, have exactly the same choices. So, of course, they're the same number of choices. You need to have a square matrix. And it's not just that they have the same number of choices, but they're the exact same choices, and the payouts are the exact same for each player if the same choices are made. An example of this is the rock, paper, scissors. Both players get to make the exact same choices, rock, paper, or scissors, and the payout for each player, we don't care which one's player 1 or player 2, the payout for each player is just 1 if that player has, say, paper and the other player has rock, because paper beats rock. The payout is -1 if, for example, you as one of the players plays scissors and the other player plays rock, because rock beats scissors. So the game has exactly the same rules for both players with exactly the same choices. Well, why does that mean that the matrix A should be equal to -1 times the transpose? Well, the transpose just interchanges the choices, interchanges the entries in, say, row I and J to the entry with, or switches the entry in row IJ with the entry in row JI. Let me say that again. The transpose switches the entries in position IJ, that means row I, column J, with the entry in position AJI, row J, column I. That just means the two players are switching, which they do. And we multiply by -1 because when you switch the two players, you still have a payout from, say, the one, I'll call one the winning one and the other the losing one, when you switch the role of the players, because the matrix for a two-player zero-sum game is always created to have a positive number, meaning a payout from player 2 to player 1. When you switch their roles, in other words, switch the row and column entries, in order to have the same payout for the same choices, we need to multiply that payout by -1 to indicate the payout is now going the other direction when we've switched the choices. An immediate consequence of that, or sorry, in notation, to say that the matrix A is minus A transpose, means Aij, this is what I just said, is minus Aji for all I and j. When I say all I and j, I mean 1, 2, 3 up to n. And in particular, that means A sub I equals 0. The entries along the diagonal must be 0, because they have to be, each entry along the diagonal has to be -1 times itself, and the only way that can happen if the number is 0. So for a symmetric game, you're going to have a payout matrix that looks something like this, where here A21 will be minus A12, AN1 is the same as minus A1N, etc. This will be true for all I and j. Here's my claim about what happens in a symmetric game, and it should be pretty obvious given what we mean by a symmetric game. I claim the value is 0. It's a fair game. And the two players have exactly the same optimal strategies. Now, in the book, you'll see a formal argument for this using the linear algebra notation. It's just a formal symbol pushing argument, and it's something you should definitely read. I'll give you a slightly different argument based on looking at the matrix for the game from the other player's perspective. What do I mean by that? Well, this matrix A for a game is always what I'll call from player 1's perspective. All the numbers, the entries in the matrix, represent the payout from player 2 to player 1. Imagine we just switch the players. If you were player 2 before, you become player 1. If you were player 1 before, you become player 2. We've already seen what that does to the matrix for the game. It changes the matrix into minus the transpose. But of course, here for a symmetric game, the matrix will stay the same. But now we have this exact same matrix, but it's representing the game from the other player's perspective. What before was from the perspective of player 1, payouts were from player 2 to player 1. Now it's from the perspective of player 2. Payouts are from player 1 to player 2. And it's the same matrix representing the game in both of these situations when we have a symmetric game. In other words, a skew-symmetric matrix. Any optimal strategy for player 1 in the original game, I claim, gives an optimal strategy for the new player 1 in this new game. Well, the new game, of course, has the exact same matrix, and this new player 1, what I'm calling player 1 prime, that's what looks like, the player that plays the rows in the new game, was player 2 in the original game. Optimal strategies are the same because it's exactly the same matrix. But in this new game, this new player 1 plays exactly the same as in the original game for player 2, because that's how we created the new game. We just said, just look at the original game from the new player's perspective. Thus, in the original game, player 2 has the exact same optimal strategies that player 1 had in the original game. This same argument says that any optimal strategy for player 2 must also be an optimal strategy for player 1. So optimal strategies are identical for the two players in this symmetric game. Why should the value equal 0 in such a game? Well, what if the value were positive? Well, in the original game, having a positive value means player 1 can guarantee at least that return. Well, what happens in the new game when we just switch the view from the game from player 1's perspective to player 2's perspective? It has exactly the same matrix, so the person who's now in player 1's position, which was the old player 2, can guarantee a return of at least v, which is positive in this game. But remember, it's the exact same game, just looked at from the other position. In other words, if the value of the game were positive, player 1 could play a strategy to guarantee an expected return of at least this positive number v, and player 2 could now guarantee at least a positive return of v to him or herself from player 1. And that's impossible. It can't be the situation that both players can guarantee a positive expected return to themselves. So this is impossible. A similar argument says v less than 0 is also impossible. So we're left with the case that v must be 0. So a symmetric game is one that just plays exactly the same for both players, the same payouts, and now we're talking about payouts from the other player to that player, regardless of which player you are, if the same choices are made. The value must be 0, optimal strategies must be the same. And we saw that, I'll remind you again, in the rock, paper, scissors game. The value certainly was 0, and the optimal strategies for both players were just 1/3, 1/3, 1/3. Here's a different example. You can see in this matrix here, it's skew symmetric. Each entry is -1 times the entry where you have the row and column switched. This one is -1 times that -1. We have -2 and 2, 2 and -2, and we have, of course, zeros down the diagonal. So as a skew symmetric matrix, this is the matrix for a symmetric game. We know ahead of time the value will have to be 0, but what are the optimal strategies? Well, what I would like to do, there are many ways you can find the optimal strategies. What I would like to do is try to use these simple formulas that we derived in the previous video lectures. The problem with that is that this matrix actually has determinant 0. The value is 0. Remember, the formulas we had in the last video lectures applied only when we had an all strategies active situation, and in those situations it would apply only when you had a value that's not 0. Here the value is 0, and in fact the determinant is 0, and we can't really apply those formulas. But we can apply them in this modified game. In this modified game, I've added 1 to each entry of the matrix. You'll see, compared to the upper matrix, I've added 1 at each and every position. This is no longer a symmetric game. Adding 1 in every position means no matter what happens, there was the original payout, plus there's $1 extra going from player 2 to player 1. You should guess what this does to the value of the game. Here we had a symmetric game of value 0. It's perfectly reasonable to think, of course, this should have value 1 because you get all the same returns, plus an extra $1 for player 1, no matter what happens. And we'll see, of course, that's going to be the case. Can we solve this game using our formulas? Well, let's see what those formulas were. Notice that the determinant of this new matrix is no longer 0, it's 25. And before we do the other computations, let me ask you to consider the following thing. If you start with a matrix whose determinant is 0, and you add 1 to each and every entry of the matrix, does that automatically mean the determinant of the new matrix will be non-zero? The answer is no, it might stay 0. You can think of many examples. I'll show you some. You could start with the matrix whose determinant is 0, like that. You add 1 to each entry, and of course the determinant stays 0. But in some cases, and you see this is one example, the original matrix did have determinant 0, whereas the new matrix has determinant non-zero. What does that let us do? Well, that means this is now non-singular. And we can apply our formulas. What formula am I talking about? Well, the value is just 1 over the vector 1 transpose A inverse times the vector 1. Remember, the vector 1 was a column vector of the appropriate size, like that. So we could compute the value like this, but that required that our matrix be non-singular and that we're in an all strategies active situation, which I haven't actually addressed yet. Before we talk about the rest of the computation, is it obvious that for the game with this matrix, it's an all strategies active situation? It might not be totally obvious. You'll see there's no obvious example of domination. And if you think about it for a bit, you'll see you can't eliminate the possibility of using any row or any column in any obvious way. But again, it's hard to convince yourself that it is all strategies active. Just like before, we're going to do the computations and see if that can allow us to justify that assumption at the end. Well, of course, here if I do the computation, 1 transpose A inverse 1, you get this, the vector 1, 1, 1 times the inverse of this matrix times 1, 1, 1. You can easily compute that either by hand or using a computer, and we get the number 1. In other words, v equals 1. That's exactly what we said was obvious for the value of this game, since we took a game with value 0, a symmetric game, and added 1 to each entry. Of course, the value should be 1. The reason we did this, of course, is because we wanted to compute optimal strategies. So how do we compute optimal strategies? Well, Q transpose, this is for player 2. The optimal strategy for player 2, at least as a column vector, can be computed by using A inverse times the vector 1, which is equal to A inverse times 1. And when you do that computation, you get 2/5, 2/5, 1/5. Similarly here, we just have our optimal strategy for player 1 was the vector 1 transpose times A inverse. Oh, and I should have said this was all divided by the value. I easily can ignore that. I'm sorry, not divided by the value, multiplied by the value. So let me rewrite that, I'm sorry. Here, the optimal strategy was just the value times times A inverse times 1. And that's what we have here. I left out the value because the value was 1 in this case. So here's A inverse times 1. And that's what gives us our optimal strategy here. 2/5, 2/5, 1/5 for P, we have the value v times the transpose of 1 here, this 1 row vector, times A inverse. And again, the value is 1. If we do this computation, we get 2/5, 2/5, 1/5. So for this new game, where we had added 1 to each entry, we can use these very simple formulas that I've written down here to compute the value as 1, and these are the optimal strategies. P and Q, of course, are both identical, 2/5, 2/5, 1/5. What does that tell us about our original symmetric game? Our original symmetric game, we subtract 1 there, we have value 0, and optimal strategies are exactly the same, because adding 1 to each entry shouldn't change those optimal strategies. You have the same optimal strategies for both players, and it's that vector 2/5, 2/5, 1/5.